In the last episode, we looked at how to store our unstructured data. In this episode, we'll learn how to run custom training jobs on Vertex AI. I'm Nikita, and this is Prototype to Production, where we go from notebook code to a deployed model in the cloud. You might be wondering, why do I need a training service when I can just run model training directly in my notebook? Well, for models that take a long time to train, a notebook isn't always the most convenient option. And if you're building an application with ML, it's unlikely you'll only need to train your model once. Over time, you'll want to retrain your model to make sure it stays fresh and keeps producing valuable results. Manually executing the cells of your notebook might be the right option when you're getting started with a new ML problem. But when you want to automate experimentation at scale or retrain models for a production application, a managed ML training option will make things much easier. Not to mention, Vertex AI training comes with additional features like hyperparameter tuning, distributed training support, and integration with other parts of Vertex AI. Running a custom training job on Vertex AI is done with containers. Don't panic if you don't know a whole lot about containers or Docker. I'm going to show you exactly what you need to know. Containers are packages of your application code, which in this case is our training code, together with dependencies like specific versions of libraries required to run your code. In addition to helping with dependency management, containers are able to run virtually anywhere, allowing for increased portability. Docker is the tool we'll use to create these containers. Vertex AI training provides a set of pre-built containers. If one of these containers meets your needs, in other words, has all the libraries needed for your use case, you can provide your training code as a Python source distribution, and Vertex AI will manage the container for you. But if your training application requires libraries that are not included in these images, or it contains code that's not written in Python, or maybe you just want better control over the dependencies, you'll want to use a custom image, and that's what I'll show you next. Now, our flowers model only requires TensorFlow, so we can actually just use the pre-built TensorFlow image. But when it's time for you to run your own experiments, you might find yourself with a use case that's a little more complicated. Plus, knowing some basics of how to containerize code with Docker is a great skill for anyone doing machine learning. Here's a quick summary of the steps that we'll take to run our training job. First, we'll export our notebook to a Python file. Then we'll update our code so that we read the data in from cloud storage and save the model out to cloud storage. Next, we'll containerize our code with Docker. And lastly, we'll launch a custom training job. Our code is all in this notebook right here in Workbench, but we want to work with the Python file instead. We can do this conversion with the nbconvert tool from the terminal. We execute the command Jupyter nbconvert, then the name of our notebook, -- to Python, and we see that we now have a file called task.py, which is the Python file equivalent of our notebook. Recall that in the previous episode, we uploaded the flowers dataset to a bucket called Prototype to Production bucket. In our training code, we want to read in data directly from that bucket. Using the Cloud Storage Fuse tool, training jobs on Vertex AI can access data on cloud storage as files in the local file system. When you start a custom training job, the job sees a directory, \GCS, which stands for Google Cloud Storage, that contains all of your cloud storage buckets as subdirectories. Not only does this make it easy to access your data, but it also provides high throughput for large file sequential reads. So to access the images in our bucket, all we need to do in our code is set the path of our data directory to be /GCS/ the name of our bucket /flower photos. But we don't just want to read data from cloud storage. We also want to make sure our trained model is saved to cloud storage. That way we can access it later for deployment and predictions. You might be used to calling model.save and passing in a local path. When we launch this training job, it's going to run on a machine we won't have access to after the job completes. So we don't want model.save to be a local path. Instead, we want it to be a path in cloud storage. So let's update our model.save path to the name of our bucket /model output, which will update our save model artifacts to the same bucket in a different directory. Okay, our training code is ready, so it's time to containerize it. Let's return to the terminal and structure our application. First, I'll create a directory called flowers, and within that, a directory called trainer. Trainer is where all of our training code will go, so I'll move the task.py file there. Then, from the root of the flower directory, we'll create our Docker file. Let's review what we just did. Our application looks something like this. Remember, all of our training code is in the trainer directory in the task.py file. In this example, we only have one Python file in our trainer directory, but for a more realistic example, you would likely have additional files. Maybe you've got one called data.py, which handles data preprocessing, and one called model.py, which just has the model code, etc. In our Docker file, we'll write a series of commands, which is what the Vertex AI training service will execute. Let's take a deeper look at the syntax. The from command specifies the base container image, which is the parent container that the container we create will be built on top of. As our base container image, we'll use the TensorFlow Enterprise GPU Docker image since it comes with all of the packages we need. The workdir command specifies the directory in the container where subsequent instructions are run. The copy command copies the trainer code to the Docker container image, and if you wanted to add any additional libraries, you could use the run command to pip install. But we don't need anything additional for our example here. Lastly, the entry point command sets up the entry point to invoke the trainer. This is what will run when we start our training job. In our case, that's executing the task.py file. And that's it. With this formula, you know enough to start writing Docker files for your training code. Now that the Docker file has been written, we need to build our container and push it to Artifact Registry, which is a place for storing container images in Google Cloud. We'll start, etc. In our Docker file, we'll write a series of commands, which is what the Vertex AI training service will execute. Let's take a deeper look at the syntax. The from command specifies the base container image, which is the parent container that the container we create will be built on top of. As our base container image, we'll use the TensorFlow Enterprise GPU Docker image since it comes with all of the packages we need. The workdir command specifies the directory in the container where subsequent instructions are run. The copy command copies the trainer code to the Docker container image, and if you wanted to add any additional libraries, you could use the run command to pip install. But we don't need anything additional for our example here. Lastly, the entry point command sets up the entry point to invoke the trainer. This is what will run when we start our training job. In our case, that's executing the task.py file. And that's it. With this formula, you know enough to start writing Docker files for your training code. Now that the Docker file has been written, we need to build our container and push it to Artifact Registry, which is a place for storing container images in Google Cloud. We'll start by defining the path in Artifact Registry where we want to store the container image. Then we can call Docker build, and when our image is built, we'll push it to Artifact Registry. If you missed any of these commands, don't worry, I've written them all out in the code lab linked below. Once the image is pushed, we'll be able to see it in the console under Artifact Registry. Again, this container image has all of our training code and the dependencies that we need. So now we're ready to launch our training job. Under the training section of the console, select Create. Select Custom Training Advanced as your training method. Give your model a name. In the container settings, select Custom Container, and then we'll add the path to our container in Artifact Registry. We specify our compute, and we'll skip the prediction container step for now and do that in the next episode. Finally, we click Start Training. If you'd like to learn how to launch training jobs using the Python SDK instead of the UI, check out the code lab linked below. Under the Custom Jobs tab, we can track the status of our training job. We can click on the name to see the details on the configuration, and when it's finished, we can see the logs. We'll also see the saved model artifacts here in our cloud storage bucket. In this episode, we talked about the benefits of a managed training service and walked through the steps required to train custom models on Vertex AI. In the next episode, we'll use this model to get low latency predictions with the Vertex AI prediction service. Be sure to check out the code lab linked below, which provides detailed instructions on everything we covered today. And don't forget to like and subscribe for more great content, and I'll see you next time. Welcome to Prototype to Production, where we go from notebook code to a deployed model in the cloud. I'm Nikita, and I'm going to show you all the foundational concepts you'll need in order to build, train, scale, and deploy machine learning models on Google Cloud. We'll cover the basics and also dive into more advanced topics like hyperparameter tuning, distributed training, and experiment tracking. We'll use an image classification model as our main example for this entire series, but many of the concepts covered are still very applicable to other data and model types. In this episode, we'll start by talking about the benefits of running machine learning in a cloud environment. Then, we'll look at how to use notebooks on Google Cloud. If you're anything like me, your machine learning journey probably starts in a notebook. Maybe you're running Jupyter in a local environment, or maybe you're using Colab or a Kaggle kernel. But while experimentation in notebooks is great, it's easy to hit a wall when it comes time to scale those experiments. Suddenly, your concerns are far more than just getting the highest accuracy score. What if you have a long-running job, want to do distributed training, host a model for online predictions, or maybe your use case requires more granular permissions around security and data privacy? What's your data going to look like at serving time, and how will you monitor the performance of your model over time? For all of that, we turn to the cloud. Let's jump in and see how all of this works. Step 1 is to set up our environment. We'll use Vertex AI, which is Google Cloud's managed machine learning platform. From the Vertex AI section of the Cloud Console, select Workbench. Vertex AI Workbench is the place to go in Google Cloud if you want to work in a notebook. So if you're already using notebooks, this environment will feel familiar. Under Manage Notebooks, select New Notebook, give the notebook a name, and under Permissions, we'll run our notebook as a service account. Then, under Advanced Settings, you can customize your notebook by providing your own Docker image, changing the hardware profile, and adding GPUs. Workbench notebooks also shut down automatically after a period of inactivity, so you won't incur additional charges when you aren't using the instance. To enable terminal access, just select this box at the bottom. And once our notebook is ready, we'll see this Open Jupyter Lab button turn blue. The launcher shows the different options you have when creating notebooks. Workbench provides multi-kernel support, so you can create notebooks for TensorFlow, R, PyTorch, a custom environment, etc., all within the same instance. And when I say kernel, I just mean the managed environment where your notebook runs. They come pre-installed with common data science libraries, but you can also pip install additional libraries that aren't included by default. If I click on the TensorFlow 2 kernel, this will open up a notebook that comes pre-installed with TensorFlow, as well as other libraries that are useful for data science. Workbench managed notebooks also come with Git integration, so you can make use of version control and even sync your notebook's Git repo with the remote GitHub URL. You can change the hardware profile of your instance and add GPUs, so this means you can test your code on a smaller and cheaper machine and then modify the hardware when you want to run a longer experiment or boost the training performance. This sets up our deep learning environment where we can explore data, train models, and interact with other Google Cloud services. But more on all of that later. In this episode, we took the first step in getting from prototyping machine learning in a local environment to production machine learning in the cloud. We learned about Vertex AI Workbench, which is the place to go in Google Cloud if you want to use a notebook. If you're interested in running your own Workbench notebooks or testing this out for yourself, click on the tutorials linked in the description. In the next episode, we'll learn about storing data in Google Cloud for machine learning. Don't forget to like, subscribe for more great content, and I'll see you next time. When working on machine learning problems, it's easy to be laser-focused on the model training. But the data is really where it all starts. So today, we'll cover the basics of storing data for model training and see how to access training data from the Vertex AI Workbench notebook that we created in the last episode. I'm Nikita, and this is Prototype to Production, where we go from notebook code to a deployed model in the cloud. Before we get into the data, let's take a look at the image classification example that we'll use throughout this series. But note that if you have a different data type or prediction task, a lot of what we cover in this series will still be applicable to your use case. So here's a Colab notebook that trains an image classification model on the flower photos dataset. The dataset is in a folder called flower photos, which gets loaded directly into the runtime when I execute this cell. The flower photos directory contains 5 subdirectories, one for each flower type in our dataset. These directories contain JPEGs of the corresponding flowers. The next cells in our notebook create our training and validation datasets, define the model using TensorFlow and Keras, then train and save the model. Our goal is to take all of this code and run it on Google Cloud's managed machine learning platform, Vertex AI. But if you want to train models on Vertex AI, first you need to get your data into the cloud. If you've been working in a different environment like Colab or locally, etc., you can upload any code artifacts you need to your Vertex AI Workbench managed notebook, and you can even integrate with GitHub. In the future, you can do all of your development right here in Workbench. But for now, let's download this Colab notebook as a .ipynb file and then upload it to Workbench. If you're using something like TF datasets or downloading data off the internet, you can do that directly in the notebook, just like you would in Colab or in a local environment. So for example, if I execute these cells here, it'll download the flowers dataset directly to the instance, and we can access them that way. Or if your dataset is small enough, you could even load it directly into the instance by clicking the upload button right here. Now that we've downloaded the data, we can run through the rest of the cells in this notebook. And there you go. You're training a model on Google Cloud. Now this might work for experimentation, but for something more production ready, you probably want to store the data within your project in a centralized location instead of directly on the machine where your notebook is running. And that's what cloud storage is there for. Cloud storage is Google Cloud's object storage, meaning you can store images, CSV files, text files, saved model artifacts, just about anything. Cloud storage has the concept of a bucket, which is what holds your data. Everything you store in cloud storage must be contained in a bucket, and within a bucket, you can create folders to organize your data. Each file in cloud storage has a path, just like a file on your local file system, except that cloud storage paths always start with gs://. So here in the UI, I've created a bucket called prototype to production bucket. You can upload files and create folders in the UI, or you can upload files programmatically with the gsutil tool. This tool is installed automatically in Workbench, but if you want to use it to locally upload data from your machine to cloud storage, then you'll need to install the Cloud SDK, and instructions on how to do that are linked below. So let's use the gsutil command to copy the data we downloaded in our Workbench notebook to our cloud storage bucket. We add the exclamation point to execute this as a shell command, then type gsutil cp to copy. We add the -r because we want to copy the entire directory, and -m to perform a multiprocessing copy, which will just speed things up. Once the data is copied, we can check out the bucket in the UI. We can go into one of these folders and see all of the images. When you have data in cloud storage, you can often still access it using the same methods you would before. You'll just need to pass in the cloud storage path, also known as a URI, instead of a local path. So for example, if you're familiar with using TF records, you might use the tfdata tfrecord dataset class to create your dataset. You can pass in a cloud storage URI and read the data just like you would if the data was stored locally. And you could even do the same thing with image dataset from directory, which is the function we're using in this sample. In this episode, we saw how to download data directly to our Vertex AI Workbench instances for experimentation, and how to create and upload data to cloud storage buckets via the UI and the gsutil tool. Vertex AI Workbench and cloud storage are building blocks that will be a core part of our machine learning journey on Google Cloud. In the next episode, we'll learn about running custom training jobs on Vertex AI's managed training service and how to kick off a training job from a Workbench instance. Don't forget to like and in the last episode, we trained a custom model on Vertex AI. In this episode, we'll learn how to get batch and online predictions from that trained model. I'm Nikita, and this is Prototype to Production, where we go from notebook code to a deployed model in the cloud. We have a trained model that we save to a cloud storage bucket. But ML is not just about training. What's the point of all of this work if we don't actually use the model to do something, right? So just like with training, we could execute predictions directly from our notebook by calling model.predict. But when we want to get predictions for lots of data or get low latency predictions on the fly, we're going to need something a little more than a notebook. Just imagine if we wanted to process large quantities of the flower images in batches. A notebook probably isn't the best place for this. Or what if we wanted to use our model in an application where users could upload images of flowers and have them identified immediately? When you're ready to use your model to solve a real-world problem with ML, you don't want to be manually executing notebook cells to get a prediction. Instead, you can use the Vertex AI prediction service. So let's see how to use it to get both batch and online predictions. Step 1 is to get your model into the Vertex AI model registry, which is a repository where you can manage the lifecycle of your ML models. From the models section in the Google Cloud Console, we select the import button. We give our model a name, and then we'll select a container. We'll use the pre-built TensorFlow container, but if you're curious how to create custom containers for predictions, check out the resources below. Then we need to specify the path to our saved model artifacts in cloud storage, and then we can click Import. This can also be done in the SDK, and you can find the relevant code snippets in the code lab linked below. When the model has been imported, we can see it here in the model registry. You can see that the version ID is 1, but if we were to retrain our model, we could maintain multiple versions of the same model. There are 2 types of prediction jobs we can run in Vertex AI: batch and online. Batch prediction is an asynchronous request. It's a good fit when you don't require an immediate response and you want to process accumulated data in a single request. On the other hand, if you wanted to get low latency predictions from your data passed to your model on the fly, you would use online prediction. You can get batch predictions once you've uploaded your model to the model registry. But to get online predictions, you'll need to take an additional step and deploy the model to an endpoint. This associates the saved model artifacts with physical resources for low latency serving. To deploy the model, I'll click this icon on the right and select Deploy to Endpoint. We give the endpoint a name, specify the compute, and then we can click Deploy. Note that there are some other features I skipped over, like auto-scaling and traffic splitting for when you want to roll out new models, but for simplicity, I'm using all the defaults for now. Again, all of this can be done with the SDK, so definitely check out the code lab below if you prefer writing code to using the UI. When the model is deployed, we can hit it like any other REST endpoint. This means we can call it from a cloud function, a chatbot, a web app, etc. For demonstration purposes, we'll call this endpoint from Workbench. Let's return to our Workbench instance and we can open up a new notebook. I'm also going to upload a flower image to our instance so we can test our model. We'll import the Vertex AI Python SDK, and then we defined our endpoint, specifying the project number and the endpoint ID. You can find your endpoint ID in the endpoint section of the Cloud Console. And you can find your project number on the home page of the console, but note that this is different from the project ID. When you send a request to the endpoint, the request is received by an HTTP server. The HTTP server extracts the prediction request from the HTTP request content body. The basic format for online prediction is a list of data instances. These can be either plain lists of values or members of a JSON object, depending on